So what does this mean then? Well, we'll put a 1 over here. It means that I essentially make B5 an output, right? Okay, because you want to do a test program that's going to blink a LED. So we have, and there is on your current Atmega 328 P Pro kit, your board, you actually have a LED, and this is the pin that connects to that LED. So you should already be able to see what's happening. So let's see, we have an infinite loop, and we are going to check, in this particular case, the button status. You also have a button on your little board that you have bought already, and we're going to figure out whether the button is pressed or not. Now, a press means a low voltage and should be read in as an input as a bit 0. If you release it, it will be a high voltage, and you will actually see a 1 in your pin register. And look here, I'm looking at my pin register, pin B, and I have this strange formula. So let's explain what that means. So first of all, the LED is connected to the 5th pin of port B, and the switch is connected to the 7th pin of port B. Notice that by default DDRB is set to all 0, so after this particular instruction the LED pin is set as output, and the 7th pin of port B is still an input, which is connected to the switch. Now, what does this mean? Let's look at this instruction. We see this expression really means whether the expression is equal to 0. So what does that mean? Well, in here we really work with a register, right? Pin B has 8 bits, and I'm going to add in another 8-bit value, which is the one left shifted over pin B 7 positions. So I'll get this expression over here is going to be 8 bits. When I compare it to 0, then I compare this to whether all of the positions are equal to 0. So let's have an example. So if I look at this particular guy, I see pin B, and if I add it with a 1 shifted over pin B7 positions, I effectively only am interested in the 7th position, because this particular value has all zeros over the first, the position 0, 1, 2, 3, 4, 5, 6, and has a 1 on the 7th position. If I do the AND operation, that means that all of those will become 0, and only the last bit over here is being copied over from pin B. So it's either 0 or 1. And if you think about it in integer representation, this would be 2 to the power 7, would be 128, and this would be 0. So if I'm comparing this over here, I'm actually talking about, is that expression equal to this guy or not? Anything else, like this for example, which is not equal to 0. So that's how you should think about this. Now let's have a look. So if this actually holds, then what that means is that that 7th bit is equal to 0. That in turn means that the input from the switch that I receive is a 0, that means that it is pressed. Then what am I doing? I'm going to do this particular thing over here. I'm going to switch off the LED. How do I do it? I have this compound instruction, and I said that this means that I clear the bit on position B5. So I make that particular bit, the 5th bit, in port B equal to 0, right? And that means that I'm switching it off. So, else, then apparently I've not pressed it, and I'm switching on the LED. So if you push it, the LED goes out. If I release it, the LED should go on. And how do you program that? Well, with a compound instruction that says I'm only setting the B5 pin, that position, to a 1 in this port, meaning that I will turn the LED on. So the LED is on if I output a 1, or high voltage, and off if it's a low voltage, that is 0. The switch is a little bit different. If I press it, I see a low voltage, that's a 0, and if I release it, I see a high voltage, that's a 1. So that's what's going on over here. Alright, so you guys will be using the delay library actually in this first laboratory, so you will explicitly mention when that's not allowed anymore, but for now we have not even talked about interrupt service routines, or not taught you how can you avoid a delay library. But the point is here that the delay library provides some functionality like this, that you can introduce a delay of a certain amount of microseconds or milliseconds, and this delay library that you're going to use actually needs to know the frequency of your CPU. So what you need to do is, you need to, actually this is the same, well, it's a different processor, I should have changed that. But in any case, if you would use this particular processor at the 60 megahertz frequency, for example, then you would need to define the FCPU, that particular keyword that you're now going to define yourself, to this particular number, which represents the 16 megahertz frequency. And you will do something similar in your code. You will include an expression like this. If you include this particular delay library, which you will, if you do these first few tasks, you will create a blinking LED, so you need to know for how long you need to wait before you turn on or off a LED. Alright, so but here is what I would like to stress though. In the future we will only use the delay functionality in order to define the access functionality for example an LCD screen. The LCD screen itself is quite a complex system on its own, a complex hardware module on its own. I cannot just, for example, immediately write a 1 at a certain pin and then write immediately after a 1 at another pin. According to the spec of the LCD screen, I need to wait till the hardware has settled for at least a certain amount of microseconds. So you will notice that in this library, later when we're going to talk about that, you will actually need to wait for a certain small amount of delay here and there. And later on, when we talk about ISRs, we will actually go into to remove those delay functionality. So that will be quite interesting. Alright, so a test program for blinking the LED would be something of this kind. So again, you will be able to use this test program once you have hooked up say your LED and stuff like that, but this is another test program. Here it is. This one is setting again bit 5 to an output. You have an infinite while loop, and I'm going to wait for a second in between. So I'm turning it on, the LED connected to that pin B5, and then turning it off, and I go through this while loop. Very simple test program to see how it all works. So that's what you will do first, and then later on you will hook up more. Oh, that's it. Yeah, so I think this is where we are. So it's quite a short lecture. So for the next lectures, we're going to dive into the UART first, and then later on we will do the LCD screen, all in this particular block. Then in block 2, so in 2 weeks from now, I will explain to you interrupt service routines, how to work with timers, and I'll show you how to deblock, meaning that you remove all the delay functionality and so on from the UART. You're going to program that too, and then yourself you need to figure out how you do that for the LCD screen. Of course, I will give you a lot of hints on how to think about it, but that's going to be quite an interesting task. So that's how all of this connects for now. And after that, we will add in many more peripherals like a PWM signal and so on, and other stuff. So I think that's it. So yeah. So I'll see you in the laboratory. All right. Any questions, by the way, for up to this point?